Hi guys, this is Mr. Mgala again with alternating current circuits by Mr. Mgala. But in this series, we're going to start bit by bit trying to familiarize ourselves with some circuitry, and if we possible also try to see if we can look at some of the circuitry elements that are very key in trying to define circuits that are related to this alternating currents. Remember that when we deal with alternating voltages and currents, we have these voltages that are changing with time, and so we want to see the behavior of these currents and voltages when they are applied, let's say, to a load that is resistive, or they are applied to other types of loads that I'm going to discuss with you as we go along. All right, now I want to mention that in this preamble that the circuits, the behavior of the voltages and currents in an AC circuit might not be like that of a DC, because we're dealing with things that are changing with time all the time. So you need to be very careful how you analyze and be very careful how you adopt certain things. So in this, I'm going to show you the basics, and then as we go on, I'm going to build up on that. Real quickly, we are going to look at the AC circuit. Now, an AC circuit consists, if you look at an AC circuit, now an AC circuit consists of a combination of circuit elements and an AC generator or a source. So now the output of an AC generator is sinusoidal and varies with time according to the following equation. Now guys, this equation might not be so much of a difference over what I showed you. Don't worry about this change. We just it's just showing you that this is changing with time. And then we have also the maximum value of the, and these things you've actually seen this equation, but not of course in these changes. But these changes should not really confuse you, because it's just one and the same thing. So we can have also a sine and then a 2 pi f, which is just like omega f. Of course, we know that this is the instantaneous voltage and this is the maximum voltage of the generator, and we know that the F is the frequency at which the voltage changes. Now, when we talk about the resistor in an AC circuit, now I've shown you guys the resistor before, but other elements I'll show you in the end. So what we always want to check is what is the behavior of this waveform when the circuit is let's say, for example, when the circuit has got the resistive load, or when the circuit has got other types of loads such as the capacitive or inductive. We want to know that. So when I show you now, when you say a resistor, consider an AC circuit consists of an AC source and a resistor, right? Now the graph here shows the current through and the voltage across the resistor. Now what normally happens here, if you look at this graph, now this graph would correspond to the current, and also this graph would correspond to the voltage. But one thing that you need to appreciate, that the behavior of the AC circuit when it's connected to a resistive load, these currents and voltages, they actually behave pretty much in what I'm showing you right now. In other words, the current and the voltage, they are in phase. Now what we mean by phase, well, they both start rising from zero. You can see here that we've got the starting point as the same, and when this one reaches maximum, that's when even this voltage inside reaches maximum. They come to zero at the same time, and they all maintain the same period, also come there, and you can really conclude that whenever a generator is connected, an AC generator is connected to a resistive load, then it means the voltage and the currents are actually going to be in phase. Now the current and the voltage are actually in phase, and in phase it means there's no phase shift between the two waveforms. Now more about resistors. So the direction of current has no effect on the behavior of the resistor. The rate at which electric energy is dissipated in the circuit is actually given as that. So this has to do with power, guys. If you say power is equal to I squared R, where I is instantaneous, the heating effect produced by an AC current with the maximum value of I max is not the same as that of a DC current of the same values. The maximum current occurs for a small amount of time. Now, RMS current and voltage. The RMS current is the direct current that will dissipate the same amount of energy in a resistor as it is actually dissipated by the AC. Alternating voltage can also be discussed in terms of what RMS. Now, Ohm's law in an AC circuit. So RMS values will be used when discussing AC current and voltage. So remember, these RMS values, even in my previous, they're actually calculated, and these could be used when discussing AC currents and voltages, right? That's the point. Now, AC ammeters and voltmeters are designed to read RMS values. Just like I told you before in class, they're designed to read RMS values. Many of the equations will be in the same form as in DC circuits. All right. So Ohm's law for a resistor R in an AC circuit, Ohm's law gives you that. Right. So the voltage RMS can actually be calculated by current RMS times the resistor. Okay. Also applies to the maximum values of V and I. Now, guys, I need you to understand when we deal with Ohm's law here, we may be dealing with the RMS values, and we can also apply Ohm's law when we look at the maximum values such as the VM and the IMs, right? So guys, you need to understand that. Now, capacitors in an AC circuit. Now, the capacitors, these are other types of loads as well, and I'll be able to show you at the end of these lecture notes that there's this thing called the capacitor, and again, there's a way this AC circuit would actually behave in a capacitor. So consider a containing capacitor and an AC source. The current starts out at a large value and charges the plates. So there is initially no resistance to hinder the flow of current while the plates are not charged. As the charge on the plate increases, the voltage across the plates increases and the current flow in the circuit decreases. All right. Now, more about the capacitor. Now, if you look at the capacitor, and this is actually the behavior of, like I said, the current waveform and actually the voltage waveform. So we saw in the resistive load how the behavior of this were. Now, in a resistive load, we said that the voltage and the current are actually in phase, but you can see here they're actually out of phase. Now, this is what you need to remember about the capacitor. You need to remember, you can see this voltage waveform is actually leading. This is the current that is leading. Now, what do we mean by leading? So what happens if you extrapolate this and it goes, it's actually to the left of this voltage waveform. That just tells you that the voltage in a capacitor is lagging as a waveform, because if you extrapolate this, you can see it's lagging. But also, not only that, you can even see here, if we take this point and we can take that point, you can see that this purple line is actually ahead of this in terms of this. Now, I want to mention that in a capacitor, this is standard. The current actually leads the voltage by 90 degrees. So this is what happens. It's a gospel truth. You need to take it. That's what happens in a capacitor. The voltage lags the current by 90 degrees. The voltage across the capacitor lags behind the current by 90 degrees, meaning that the current leads by 90 degrees. Now, there are some terminologies that you need to begin to understand. When we talk about the capacitor actually is measured in farad. And we'll talk about this in detail when we start looking at some sample examples. But you need to understand that there is what we call the capacitive reactance and the Ohm's law. So when we want to apply Ohm's law in relation to the capacitor, what we're dealing with, we're not taking its value as in farad. We're supposed to look at what we call the reactance of the capacitor. And now the reactance of the capacitor is like the resistors of the capacitor, and I'm going to talk about that. The impending effect of a capacitor on the current in an AC circuit is called the capacitive reactance, and it's actually given by, oh guys, I didn't put here what it is given by, but I just don't have a right, but I thought I'd written it down, so mistakenly I removed it. But it's given by the XC. Now the XC, we can't see it here. Oh my gosh, I don't know what happened here. Okay, so I'll fix it, guys. So it's actually XC. You can't see it here, but it's equal to 1 over 2 pi FC. You can see here, it's not, you really need to have your eyes, but it's actually XC, which is the capacitive reactance, is equal to 1 over 2 pi FC. It's actually 2 pi FC, or is 1 over omega c, which is good as 2 pi fc. So when F is in hertz, where F is in hertz, C is in farad, and XC will be in ohms as well. So Ohm's law for a capacitive and an AC circuit is given by, we can say that the RMS value, I talked about the RMS value is equal to current RMS times XC. Now guys, I'll come and fix this, but just if you take your eyes, you see some XC and 1 over 2 pi FC. Now we'll come to this, no big deal about it. Now you can see, like, so when we deal with the capacitive circuit, that's what we say, and the formula has been given, and Ohm's law can apply to the RMS values. And by the way, we can also apply Ohm's law to the amplitude values as mentioned. Now when we deal with inductors in an AC circuit, now consider an AC circuit with a source and an inductance, right? Now inductance, how the inductor looks like, I'm going to show you guys, but this is a typical waveform that you get when we deal with the inductor. So if this is the voltage waveform, and now this is our current waveform, and that's how it looks. Looks the amplitude is quite high, and I'm going to explain in detail why that is the case. But right now it's very important for you to understand that in an inductive circuit, the voltage actually leads the current by 90 degrees. Now guys, anything that is to the left of the particular waveform is actually leading, and anything that is to the right is actually lagging. So you can see here that this voltage waveform, which is the voltage, actually is ahead of this purple line. If I take this 0, and that is the 0 point, so this point is ahead of this point, it's more to the left, therefore it's actually leading the current by 90 degrees. And if this is the angle, really, if you have to evaluate it, you actually find out that in an inductive circuit the current lags the voltage by 90 degrees. Now guys, we have also what we call the inductive reactance and Ohm's law. So the effective resistance of a core in an AC circuit is called its inductive reactance, and it's actually given by XL, which is in a capacitor is given by XC is equal to 1 over 2 pi FC, but here as an inductor is actually given by XL 2 pi F or omega L, where F is in hertz, L is in Henry, XL will be in ohms, right? So Ohm's law can also apply to the RMS values. Now let's discuss a bit about on the RLC circuit. The RLC circuit. Now guys, if we've been talking about the C and the L and the R, and you haven't seen them, but these are the symbols. Actually, you can see here there's a resistor right here, and there's an inductor right here, and there's a capacitor right here. So now what we say about the RLC series circuit, the resistor, the inductor, and the capacitor can be combined in a circuit actually. So the first thing that I want you guys to understand and appreciate is that in this case, of course, we're showing you that there's a voltage drop across the resistor, there's a voltage drop across the inductor, there's the voltage drop across the capacitor, and this is actually the supply voltage. Now the resistor inductor can be combined in a circuit. Now we are able to combine them in series. By the way you treat this is not the way you treat it in a DC circuit. So the current in the circuit is the same at any time and varies sinusoidal with time. So you can see here, if we have a series circuit, there's the same current that is flowing around the loop, and it varies sinusoidal with time. Current and voltage relationship in an RLC circuit. Now if I have to look at the behavior of the current, voltage, and of how the currents and voltages would behave in an AC circuit, this is what I would say. So if this is my current profile in paper, then if we talk about the voltage drop across the resistor in this series AC circuit, then we are saying that this voltage is actually in phase with the current. You can see they're both starting at 0. This was also starting at 0. You can see that ends at that. So they're in sync. All right. But now if we talk about the voltage, if this is current as a reference, because it's the same, it doesn't change. But when you see the behavior across across. You can see here, because it's an inductive circuit, this voltage right here will actually lead the current. You can see if we take it further again, it's actually leading, the voltage is actually leading the current. It is to the left of the current. You can see that the current is actually going to be overtaken by this. So the voltage actually leads the current by 90 degrees. Now if you see, if it's the capacitor, if this is our reference voltage or reference current, sorry, then definitely current is ahead by 90 degrees. You can see here that the current is in front while this is lagging behind. Right now, generally speaking, you can see that also the voltage supply will actually in a way try to lead the current, the resultant voltage, because now this voltage will be as a result of these three. Okay, so if we algebraically sum them, we should have a voltage waveform that looks like that, and I'll show you in the next point. Now there's this very important concept. It's called the concept of phasor diagrams. Now you need to understand that when we are dealing with, let's say, series AC circuit, the way the voltage is behaving here and the way the voltage is behaving here and the way the voltage is behaving there, they are actually out of phase. And so since they're actually out of phase, that you can actually choose to represent the voltages across any of those of the actual voltage, which is the summation. You can choose to represent it in what we call phasors. Phasors are a neat way of representing these voltage drops so that we are able to really account for them effectively. So to account for different phases of the voltage drops, vector techniques are used. So this is represent the voltage across each element as a rotating chord, a phasor. The diagram is called a phasor diagram. So we have the x and the y axis here, and what you see here is actually the actual supply voltage itself, and this becomes the maximum voltage. But let's just try to see. This is how a phasor looks like. Let's just go back a little bit, and you can see here this is the angle that this supply voltage is actually moving as a phasor. But guys, I didn't show you, actually you can represent any voltage in terms of the its phasor diagram, but then we'll learn it even in this. Let's try to look at this. The phasor diagram for RLC circuit, how does it look like? Because you need to map them on a phasor so that you know exactly what's going on. So for example here, guys, we can say that the voltage across the resistor is on the x-axis. If we take the voltage across the resistor, and we know that the voltage, and if we took also the current in the same direction, then we know that the voltage across the resistor would be in the same phase as the current, so that doesn't change, and so therefore we put it in the x-axis. But I want to mention that since this is also the current phase, then we know that the voltage across the inductor would actually lead this current, which is also the phase here, because remember that this voltage is caused by IR. So therefore we're going to move 90 degrees upward to plot the voltage across the inductor, because the voltage across the inductor actually leads the current by 90 degrees. And here we shall be able to plot the voltage across the capacitor with reference to this current, which is on the x-axis. We can see that the current leads the voltage across the capacitor by 90 degrees, meaning that the capacitor voltage lags by 90 degrees. And this is exactly what I'm explaining right here. Now this is what we call the phasor diagram that you need to, of course we are continuing the phasor diagram, but phasors are added as vectors to account for the phase difference in the voltage. So we use phasors to add and also to account for the phases. Now if you see here, guys, you can see here that we had in the previous example, we had in the y-axis, in the x-axis we had that voltage, and in the y-axis we have this. Now I want you to understand very well. Now if we are dealing with a circuit like this one, Then there's need to find, so what is the supply voltage? It is the summation of all of this, but you don't sum them directly. How do we sum them? We sum them in this case in form of a phasor. We need to understand the fact that this is really our resultant voltage, right, as a result of the summation. But how do you do it? There is a voltage that is showing that is in the upward and the up x-axis, in the y-axis, and there's one that is showing the lower axis. Actually, though it is showing this way, you can bring it this way. But now what that means is that we can actually subtract, because these vectors are opposite. They are opposite, right? So there's a vector that is going there and there's a vector that is going there. So we may find the resultant vector between these two, meaning that we can subtract that one and subtract that one. And if we do, we'll come up with a vector that is a bit shorter, right? That is changed, that is the vector plus the inductor minus the capacitor. We can now from here draw where the resultant vector is going to appear. So we can see here that this and that are on the same line, and so the net y component is just a subtraction of the two, and we can close the path by to find the resultant vector. Now this from the phasor diagram, the voltage are not in phase, so they cannot simply be added to get the voltage across the combination, right? Oh guys, I missed something here. Some words that have been missed, so fix it. That so theta could be the phase angle between the current and the maximum voltage. Now we could have actually this as the theta, that is the angle between this and the maximum voltage. Now the impedance of a circuit, now from the same voltage, now we can actually also derive from this same triangle, which is the voltage triangle. Actually we can also derive the impedance triangle. Now guys, you know that if I took this one here, this current right here, if I put it in terms of the RMS values, guys, I just don't have a writing pad. I'd have shown all of this, but just understand and appreciate that in terms of the RMS values, this can be calculated as RMM, I times XL minus I times XC, right? So, and then this one can be IR. If you knock out all the I's in all of this you can find yourself in a situation where you write this one as XL minus XC, and then here we can have just R. Okay, so now that if we come to such an arrangement, then we are actually forming what we call the impedance Z, and this impedance is the total resistance of a circuit in AC. Now the impedance is a word that we use when we're trying to define what our the way we call our resistance in AC. We don't call it mainly as resistance, we call it as an impedance. Now you get used to the Z itself very soon, but right now suffice to say that if I get the voltage triangle, I can easily transform it into the impedance triangle. So I can multiply everywhere by current, and I can still get back to my previous diagram that I showed you. But suffice to say right now that this is what you get in terms of the impedance triangle. So we have the Z here, which is this one right here with the angle, and we've got the resistor underneath there. Now there's some equations that I should have shown, guys, and I'll be able to show you in the next class, because you can see here I just messed it up, because Z in terms of magnitude can be calculated the same way. You can say that Z squared is, because you can just use Pythagorean theorem to calculate what the value of Z is. Now I'm gonna show you I think I don't know how I missed it right here, because there's some formulas that I failed to capture, but right now suffice to say that Z is equal to the square root of R squared plus XL minus XC squared, open and close bracket XC, and then you can also find this angle. The angle, this angle can be found using the TOR, where you can say the tan inverse of XL minus XC divided by R. Let me show you this in the next class. in the impedance, an Ohm's law. So Ohm's law can be applied in the impedance which is the total resistance. We can also apply that by using that. Now guys, I'm gonna show you right here right now that these are the summary of circuit elements, impedances and phase angles. So what are we saying? We're saying if you just have that, you have this is R, and that is the phase angle is 0, and you understand what I mean, right? So there is the capacitor here, and that the reactance for the capacitor is the XC. And actually, why are we writing minus 90 degrees? Well, minus 90 degrees because we know that if we take the X or Y plane, the capacitor is actually lagging on the lagging side. And this is an inductor, and we take XL, and if we take it on the impedance triangle, we can see that the capacitor all it leads. Now I want to mention, guys, that to calculate the resultant impedance of maybe when you have a resistor and a capacitor, it can be calculated as the square root of that R squared plus XC, right? So I'll show you how we draw the phasor diagram for all of this. But negative between, so here we can say that the resultant, which is this one here, the resultant is actually negative. The resultant vector or impedance is going to be negative, and it's going to lie between minus 90 degrees and 0. Okay, so I'm going to explain all of this. If we have all of this, again, we can have positive between 0, and so this is the resultant impedance, which actually its resultant impedance, which is a vector, is going to lie between 0 and 90 degrees. Now if we have an RLEC circuit, guys, the behavior, this is what I was explaining to you, that the resultant Z, which is the impedance, has to be calculated this way, and it's negative if XC is greater than XL, and it's positive if XC is greater than XR, is less than XR. Now let me conclude in AC, and this is just a surface analysis, and I'm going to dive into the specifics as we go on, but let me just explain and conclude that to calculate, so problem solving for AC circuit has to do with calculate as many unknown quantities as possible. For example, find XL and XC. Be careful of units. You need to be careful of this. Apply Ohm's law to the portion of the circuit that is of interest. Determine all unknown and ask for problems. Now, guys, we need to understand that power losses are associated with capacitors, and pure inductive analysis. In a capacitor during 1/2 of a cycle, energy stored. No power losses are associated with capacitors and pure inductors in AC circuit because they have this charging and discharging mechanism, which is explained by here. Because in a capacitor during 1/2 of a cycle, energy is stored, and during the other half of the energy is returned to back. In an inductor, the source does not work against the back EMF of the, and the energy is stored in the inductor. But when the current begins to decrease in the AC circuit, the energy is returned to the circuit. Guys, I would like to thank you for viewing this overview, and I'm gonna dive into the intricates as we go on, and I'd like to thank you for viewing.